Hello, for this lesson we are talking about scientific notation. For scientific notation there are a couple of rules that we need to remember. First of all, the form that scientific notation will take is a times 10 to the nth power. And what that means is that we're going to have some value here. In examples 3 and 4 we see scientific notation. And there's going to be a number or a coefficient out here. And that number is going to follow these rules. And the rules are that 1 will be less than or equal to a, but it will be less than the number 10. So the number could be 1 or anything above 1 until it reaches 10. It cannot equal 10. And then when we're talking about the nth power, the n will just represent some integer. So that's whole numbers or the negative version of the whole numbers. We also can remember some rules about the power of 10 and negative exponents. For example, 10 to the second power equals 100. 10 to the negative second power is like saying 1 over 10 to the second power, which would be the same as 1 over 100. And what that's going to help us with is, with scientific notation, since it's always going to be 10 to some number, some integer, then we're going to look at that and we might say, okay, well if it's a positive integer, well that's always going to be multiplying a by something like 10 or 100 or however many power, whatever that power is, it's going to multiply it by that and it's going to get larger. While if it's a negative exponent, well that's like multiplying it by something like 1 over 100. And just simply by the power of 10 rules that we know, if you divide something by 10 or 100, what that's going to do is it's going to make it smaller and you're going to move the decimal over. So let's look at some of the examples here. So one thing that you may be asked is, turn a certain number into scientific notation, right? This is not in scientific notation in any way, shape, or form. What I need to do is I need to change our number to be between 1 and 10. Remember, it could equal 1, but it could not equal 10. So what I would need is, my a is going to be 2. Okay? Because that is all I'm giving here. I have the number 2, there's nothing after it. We don't ever eliminate values other than the value 0. And what we need to do is we need to make this true, and so I could count 1, 2 place values here. Now I would move that decimal, right? And so I'll have 2 times 10, and I need to determine, will this be a negative exponent or a positive exponent? Well, if it's a positive exponent, then that means that it's going to be 2 times something that's going to make it larger. Well, for it to be equal to that value, it doesn't need to get larger, it needs to get smaller. So if it needs to get smaller, that means it needs to be multiplied by something such as this example here. So we're going to multiply it using a negative exponent. And since we moved it 2 places, we need to use the negative 2 as our exponent. For this one here, this is 9.3 million. Right, so 9.3 million. So you have 9 whole millions and then 3/10 of another million. So a couple of ways to think of this. First of all, we could simply write this out. Okay? So, right, we could write out zeros, right? The first zeros, these are our hundreds, right? Thousands, and since that's 0.3, right, it would end up being, right, this would be 9 million, 9 whole millions, 300,000. Right, so this is what we could do. We could set it up this way. And then from there we could say, okay, well let's count. 1, 2, 3, 4, 5, 6. So we would need to move it 6 places, right? We need it to stay with the 9.3 actually. And it needs to be times 10. And again, we need to decide, is this going to be positive or is this going to be negative? Well, if 9.3 is our number, do we need it to get larger or smaller from there? Well, 9,300,000 is quite a bit larger than that. So we know it's going to be a positive integer. So I moved it 6 places, which means I'm going to have a 6 as the value there. Another way to think of it is that when we're doing these come in sets of 3, right? So we always use those commas. Those are the hundreds, right? We have the thousands, millions, billions. So if we use the word million, we automatically know that it's going to be times something 10 to the 6th power. Right? And then what we would have to simply do is look at the other value, right? Plug that number in, it would be 9.3, and then million, we know that it's going to be to the 6th power. Another thing that you'll be asked to do is probably turn a number that is in scientific notation and turn it into standard notation. Standard notation is simply what we are used to seeing numbers in. So if we look at this, remember that this is like saying 5 times 1 over 100, right? We even have that written out right here. That's like saying 5 times 1 over 100. So that value is going to get smaller, and based on the power of tens, it's going to move that decimal 2 places. And since we know negative exponents, if we're multiplying something by a negative exponent here, that it is going to get smaller. So what we would do is, if our number is 5, our decimal always starts here if there is none, and we go 1, 2 over. Now, with that little swoop, there's no number there, so that means I add a 0 there, add the decimal where the arrow points, and we get the value 0.05. Again, here we have 7.2, and it's times by 10 to the 5th power. Well, what that's going to do is it's going to make it larger, and it's going to move that decimal 5 places. We're just going to continue using that power of 10 rule. Right? If we multiply something by 10, it's going to move the decimal 1 place. This is multiplying that number by 10 5 times. So that means it's going to move 5 places. So if our decimal was here, we're going to count 1, 2, 3, 4, and 5. Right? Any of those spaces that there were no numbers, we add a number, add our comma, and our answer is 720,000. Next, we have another problem that you may be asked to complete, and that is comparing and ordering values. Now, once we get these numbers into scientific notation, it's very easy to order. But before that, it might be a little more difficult to see. So the first thing we need to do is we need to say, are these numbers in scientific notation? And looking at the first value, no, it is not, because that first number, it is not between 1 and 10. It is below the number 1. So this is not in scientific notation. The second value, it is not in scientific notation because it is well over the number 10. The third value, that is in scientific notation because it's 5.3. So that's between 1 and 10. And 530, that is not in scientific notation. So 3 of these numbers we actually have to turn into scientific notation. Well, for this one, we're going to move it over 1 place value. That's all we need to do. So it's going to be 5.3 times 10. And we need to figure out what place value is that. Okay? Well, since we moved this value, we moved it to the right. Okay? And if we were normally doing that, right, in the example up here, right, in example 1, when we moved it to the right, we used the negative exponent. Well, we moved it 1 to the right, so that would be like saying negative 1. But we're already given 10 to the 7th power. So what you would do is simply say, all right, well, if it had 7, I moved it 1 to the right, so it would be negative 1. Do 7 plus negative 1. Well, 7 plus negative 1, if we have 7 and we take away 1, we have 6. So we're going to get 5.3 times 10 to the 6th power. For the next value, I'm going to be over here, and I'm going to go 1, 2, 3, right? Because I need to get this to 5.3 times 10, and now we need to determine what is our exponent with the 10. Well, this time we moved it 3 to the left, okay? And if we were doing this like we did in example 2, 3 to the left, right, we're saying that would be 5.3 times 10 to the 3rd power. But we're already given 10 to the negative 1st. So what we look at is we say, well, if this would be to the 3rd power, we say 3 plus negative 1. and that's going to give us 2. So our exponent would be 2. This one was already in scientific notation, so we don't need to even change that one. And then finally here, we get to here, we move it 2 to the left, and like we just talked about here, this one we moved it 2 to the left, which means it's like saying 10 to the second power. So it's 5.3 times 10, and well, this one would be 8 plus 2, so it would be to the 10th power. So we now have this in scientific notation. So let's see, what one of these is the greatest value? Right? They might ask you to write it in from greatest to least or least to greatest. Well, let's do this for the greatest value. And the way to tell this is simply look at the exponent value. The higher the exponent value when they're in scientific notation means the higher that number is. So since this is 5.3 times 10 to the 10th power, this is going to be the largest number. Okay? And then we just go, well, to the 6th power, that's going to be our second largest number. To the 5th power, that's going to be our third largest number. And then to the 2nd power, that's going to be our 4th largest number. Now, one thing that they might throw at you is they might have ties between exponents. Right? So what would you do, for example, if this was 2 and that was also 2? If there is a tiebreaker, then you would look at the value in the front, that A value. And the larger that is, the larger the value would be. So if this was 5.3 and that was 2.3, then that 5.3 would be the larger. So first you look at the exponents. If there's a tie with the exponents, you look at the values in front. And if those values in front were also the same, then that would actually just mean that they're the same number. The third skill we are going to test is what do we do when we're multiplying with scientific notation. And something that's handy to remember are the commutative property and the associative properties. And what this means is when we're working with multiplication problems, right, what this means is 6 times whatever's in these parentheses, so 5.3 times 10 to the negative 4th, but we know with the commutative and associative properties of multiplication that really we can rearrange these things to help us. So I don't need to turn this into standard notation in order to accomplish this. I can simply say, well, with the associative power, I could rearrange and I could say, I'm going to take care of the 6 times the 5.3 first. So rather than turning this into standard notation and then multiplying it and then turning it into scientific notation, I'm going to save a step and simply say, I'm going to multiply 5.3 and 6. Well, we can multiply that out. 5.3 times by 6. We get 8. Carry the 1. 1 and 30. There's one decimal place value. So I get the value 31.8 times 10 to the 4th. And I'm done. Well, not quite. If you'll notice, this is no longer in scientific notation because 31.8 is larger than 10. So what I would need to do is simply turn that into scientific notation. So I need to move that over one place to 30.18. We get times 10, and again we need to determine what is going to be the exponent with that 10. Since I moved it to the left, that means it's like positive 1 as our exponent. So we do 1 plus negative 4, and that would be negative 3. For this next one, I'm going to again use that same strategy. I'm going to multiply 0.3 times by 8.2. You can write that off on the side. 8.2 times 0.3. I get 6. I get 424. So 246, but there are 2 decimal places, so I put the decimal there. 2.46 times 10 to the negative 3rd. I look at it and I say, is this in scientific notation? The answer to that is yes, because 2.46 is between 1 and 10. So those are some of the problems that you may run into when working with scientific notation.